I've been with OTBe Engineering for a couple of years now. I would like to thank BTSYM for organizing this presentation with the young members of the Nigeria Tunneling Association. And thanks again, Sohawon, for this brief introduction. So the project that I will talk about today is based in Meads, which is somewhere north of London. I'm not sure how many of you have had the opportunity to come to England. For those who don't know, Thames Water is the largest water and wastewater company serving London and Thames Valley. The project consisted of a sewer remediation scheme, as the existing sewer was damaged. The main contractor for this project was Barhill Limited. The sewer diversion works involved the construction of 3 new shafts and 2 new tunnels to replace the existing section, which is concrete sewers that were discontinued. So the scope of this presentation, we will look at the ground movement analysis and the pipe jacking design for this project. The ground movement consists of calculating ground movements due to the construction of the pipes and determine if they will affect any assets that are above ground level. The ground movement due to the installation and construction of the shafts are not in the scope of this presentation. I will only give a brief overview of which methods were used later on. Finally, I will discuss how the pipe jacking forces required to install the pipes are assessed. To begin with, I will introduce briefly what pipe jacking is so that you can have a better appreciation of the type of tunnels that we are dealing with in this project. Essentially, they are a trenchless method of installing the underground pipelines or conduits without having to dig an open trench along the entire length of the pipeline. In TBM tunneling, the TBM pushes itself along, whereas in pipe jacking, the pipes and the jacks push the machine along. Pipe jacking is widely used for underground utilities and pipelines. These include water, sewage, stormwater drains, electrical cables, and so on, and is usually a preferred choice in environmentally sensitive areas. Pipe jacking has several advantages, such as being a cost-effective solution and minimizing disruption above ground level during the construction process. This diagram shows the overall setup of the processes for pipe jacking. First, we construct a launch shaft, which is built and excavated, and in this picture, this is actually a sheet pile cofferdam. Hydraulic jacks are set up and built in the shaft at the main jacking station. A tunnel boring machine, TBM, or a shield is pushed forward and excavates the soil that is removed at the back through pipes. In this case, this is the TBM, it's a shield machine here in the front. We lower the pipe section, position it in the shaft, and then the hydraulic jacks, they push the pipe horizontally to the ground while pushing against the first wall. You can see that the first wall is quite big here because it's quite an important component of the pipe jacking. If the forces that are mobilized around the pipes become too large, then we require an intermediate jacking station, which is here. And I will talk more about this interjack later. Eventually, the pipeline will reach towards the end of the drive, where there will be a reception shaft and the micro TBM is lifted up. So essentially, this is what was being used in this project, this type of construction, this type of tunnel. So this is an overall plan of the arrangement at the site. We can see 2 circular shafts, manhole A, manhole B a bit further down. Manhole A is a launch shaft, whereas manhole B is a reception shaft. These are caisson shafts that are sunk into the ground prior to excavation inside the shaft. We can see two rectangular sheet pile cofferdams. And I will talk about these more in the next slide. We can see the proposed alignment in purple, which is the new sewer. And we can also see the disused sewer, which is this gray one slightly above it. So this is the sewer that was damaged and needed to be replaced. So we created a deviated the flow in that pipe to the purple one. This old sewer has been disused now, and if my understanding is correct, it has been backfilled with ground. There are two buildings of interest close to the tunnel alignment that may be of concern. We have building A here and building B. If we take a closer look, we can see that at manhole B, we have a temporary sheet pile cofferdam, which is built here. And the purpose for this is to create a connection to the existing sewer at the junction manhole. Further upstream, we have another temporary sheet pile rectangular shaft, which is first constructed and excavated. Then manhole C is built bottom up inside this cofferdam. And there's also a cofferdam here, which is used to create a connection to the existing sewer. In this case, it's near the penstock chamber. So onto the ground movement analysis. What were we trying to do here? So want to calculate the ground movements due to the construction of the shafts and the cofferdams. Like I said, I won't go in depth for the equations involved, but I'll just give a brief overview on which methods were used. We calculate the ground movements due to the tunnel drives. We identify if there are any assets within the 1 millimeter surface contour, and we assess if the buildings identified have more than 1 millimeter settlement, whether they will be impacted. We specify mitigation measures and monitoring if required. This map here shows a satellite view of the area. We can see the tunnel alignment in red. The launch shaft is somewhere here. It's also visible on Google Earth if you go and find this place. You have a reception shaft here, which is also visible. And you have the cofferdam upstream. I believe the cofferdam downstream is also visible on this map. And buildings, the assets, so that is building B, which is a Thames Water building. We have further a bit south, we have this building here, which is the pumping station at Meads. And somewhere in this area, we have a storage warehouse. To the west, north, and east of the site, we have green areas, as you can see, from Meads Nature Reserve. So having carried out from the site investigation data for this project, we were able to determine the ground conditions at the site, and this led to this ground model. We have made ground near the surface, which is very common in England, followed by a layer of alluvium and white chalk. Within the alluvium, we have a layer of sand and gravel, and this is where the pipe jacking for this project is taking place. The diagram here shows the long section for the tunnel and shaft arrangement. You can see that the ground level is fairly flat as well from this drawing. We have the circular shafts, manhole A and B. We also have the outline of the cofferdams, which is shown for manhole C. We have the pipe jack tunnels, which in this case were glass reinforced plastic pipes. This is quite a modern, a new material for pipes, which has been used for a couple of years. It's much more sustainability. It's much lighter than traditional concrete and steel pipes. So to perform the GMA, we use the software Oasis XDisc. And I'm not sure if any of you have experience with the software, but it's fairly straightforward to use if you understand what your inputs are and what you're trying to model. So initially, you have to build this geometry in the software. This requires the coordinates of the alignment, as well as the pipe dimensions and the tunnel dimensions as well. As for the ground properties that were inserted in this model, I will discuss this in the next slide. For an initial screening, we take into account a volume loss of 1.5%, which will be caused by this tunnel construction. And this is based on guidance from Thames Water standard. So this is a drawing showing the cross-section of one of the shafts. As I said, I'm not going to delve too much into the shafts and how the ground movements are calculated, but I'm showing you this drawing. You can see the outline of the shaft, which has a series of segments or linings. So essentially, this is what is called the sunk caisson shaft. So you start from ground level, you build a jacking collar on the top of the ground, and then you start driving these rings. They are circular rings. The first ring has some kind of cutter head to be able to dig into the ground easier. But you basically jack these slowly until you reach the depth that you require. And then after that, you start excavating inside the tunnel, and then you build your base slab and so on. So to get the ground movements that is proposed with such a shaft, the method proposed by Meads and Bowers was used. These are computed separately using a spreadsheet, and then we import them on the software XDIS. In the XDIS model, the excavation diameters of the shaft were used, and the excavation depth was taken at the bottom of the Domas concrete plug. This is the Domas concrete plug. It's quite important for buoyancy and making sure there's no uplifting. But I'm not going to talk too much about this. This slide shows the cofferdam instead, the plan view, where we have the rectangular excavation. So the ground movements for these rectangular excavations, we use design curves from Syria C760, and these are incorporated in XDIS. So this can be calculated directly in XDIS. Unlike the other one, we have to compute them separately and then insert them into the software. The excavation depth for these cofferdam excavations were taken at the base of the cofferdam. I'm sure a lot of you are familiar with the ground settlement profile that is induced by a tunnel. This is a very well-known method that has been used for the past 40 years. This is based on O'Reilly and New and defines the short-term surface settlement trough, which is described by a Gaussian distribution. So we have the volume loss, which is the volume of the settlement trough, Vs, the first equation here. It's linked to the excavated diameter of the tunnel, capital D, and VL, which is the specified volume loss. In this case, it was 1.5%, as I have explained a bit earlier. Then we have the point of inflection, which is going to govern how wide or narrow the settlement trough will be. It's linked to the trough width parameter, which is an empirical constant found in the literature, and 0.4 was used for the K value for non-cohesive ground type, as recommended in the literature. And Z node is the depth to the tunnel axis. These parameters are shown on the drawing on this sketch here, which shows an example of the settlement trough. Then we have the actual S max, which takes place at the minimum point on this curve. So the height of this minimum is the S max. It is linked to the volume of the trough, Vs, and the point of inflection I, which I have described earlier. And if we want to plot this settlement profile, this Gaussian distribution, then we need to use this last equation, which is an exponential function, where y is the horizontal coordinates from the tunnel center. So after running the XDIF analysis, the following ground movement contours were obtained. So we can see that only a portion of building A, the corner here, and building B, again the corner, were found to be within the 1 millimeter surface settlement contours. Building A was subject to a maximum differential settlement of 2 millimeter at the corner, which was too small to cause any significant damage. As for building B, that corner was a cantilevered section, so there were no building foundations there, and they were found to be outside. The actual foundations of this building are therefore outside the 1 millimeter settlement contour. In conclusion, for the GMA, it was deduced that the proposed tunneling works had no adverse impact on the buildings, and therefore no mitigation measures were required. So that's it for the GMA. I'm going to move on to the pipe jacking part now. I've already given a brief overview about what is pipe jacking, the benefits, why is it suitable, and I've also given a brief description of the actual construction process. So the objectives in this case for the pipe jacking design, which I'm also presenting, is to determine the maximum force that could be resisted by the GRP pipe, calculate the minimum and maximum frictional force that will be mobilized during the pipe jacking process, and lastly, determine if any interjacks will be required. The picture below here shows a pipe section that has been placed in the launch shaft and ready to be pushed into the ground using the hydraulic jacks. We can also see the thrust wall here, which, as I have said before, it is an important part of the design because it must be strong enough to be able to sustain the jacking forces during the pipe installation. Usually the thrust wall is a reinforced concrete wall. And point to note is that this picture is not for this project. However, the pipe that was used here, I believe, is similar. I believe this is also a GRP pipe and the supplier is the same. So the soil was excavated using a micro TBM. Drive AB was found to be around 143 meters long, whereas drive AC, which was the shorter drive, had a total length of 78 meters. In this picture here, we are still in the launch shaft. We can see that the micro TBM has been lifted into position and secured, and it's ready to be pushed into the soil. Again, we see the hydraulic jacks and we see the thrust wall. And once this micro TBM is pushed in, then the pipes are pushed in one by one. This slide gives some more details about the micro TBM that was used for this project. The micro TBM had an excavation diameter of 1.88 meters, which led to an overcut of 38 millimeter, which represents the gap. The overcut, it represents the gap between the soil and the pipe. The machine is fitted with a bentonite lubrification system and also has a guidance system using lasers. This table here comes from the technical sheet of the micro TBM supplier. It gives important technical information about the micro TBM, such as diameters, weight, and length, and a few others. Usually, for larger diameter tunnels, the TBM is built for that specific project. But in this case, and for most micro tunneling projects, you have to choose the micro TBM off the shelf. We use a table like this, and we decide which one is going to be appropriate for your design. So I think you might have seen this already in the long section drawing that I showed earlier, where we had the fairly flat ground level. The tunnel alignment as well is fairly flat. There was barely a very small change in elevation from start to finish. So the depths of the tunnel drive were assumed to be constant. Drive AB had a tunnel cover of 5.4 meters, while drive AC had a tunnel cover of 6 meters. The ground level, which was also obtained from the site investigation data, was assumed to be constant at a depth of 2 meters below the ground level. The parameters for the sand and gravel layer that were used in the pipe jacking design are as follows. We have the unit weight of the soil, the angle of friction, the lateral earth pressure coefficient at rest, which is needed to calculate the horizontal stresses. There are 3 components to the forces involved during pipe jacking. We have the shear forces mobilized along the length of the microtibium, which is in contact with the ground. So the portion of the microtibium that is touching the ground, there will always be some frictional force there. We have the phase pressure, which is applied by the slurry, especially in this case, because this is a slurry TBM at the front of the microtibium. And the purpose of this slurry is to support the advancing phase. And the main component of the jacking force is coming from the frictional force developed as the pipes are jacked into the ground. This diagram here just shows you the frictional force, the phase pressure in front, the soil stresses that is leading to this frictional force. We have the pipe dimensions. This includes the length of a pipe section, which in this case was 3 meters. As I have mentioned before, as the jacking forces increase during a drive, it might come to a point where the capacity of the pipe might be exceeded. In this scenario, an intermediate jacking station will be required. The interjacks are fitted during a drive and they reduce the forces on the main jacks by pushing the pipe in front of the interjacks first, leaving the main jacks only to push the rear section of the pipes. This table here summarizes the ultimate structural capacity of the pipe, which was 6,000 kilonewtons. This is obtained from the technical data and calculations from the pipe supplier, and it accounts for an angular deviation of 0.3 degrees. This capacity also includes a factor of safety of 3.5. The angular deviation might be a new term for you, takes into account the imperfections in the pipe alignment during the construction, but it's also very important to consider when there are curved sections in the pipe, because at each connection, we want to make sure that the stress flows smoothly. There's no stress concentration in different portions of the pipe. If that's the case, we might need to consider using packing at the joints. For this project, the limiting load case was governed by the capacities of the first wall. The jacking forces could not exceed this, and these were found to be 5,000 kilonewtons for drive AB and 3,500 kilonewtons for drive AC. To calculate the shear forces mobilized at the pipe and soil interface, we considered 3 cases. We have the worst case scenario in which the pipes are not lubricated at all and the bore has fully collapsed. We can think of this case as the soil has fully crumbled and makes full contact with the pipe across the entire length. We then have the best case scenario in which the pipes are well lubricated and the bore is stable. This is usually the case when we have a moderately strong soil that can stand up for a long time. And that will lead to a gap between the soil and the pipe across the entire length. And this gap is usually filled with a lubricant. In reality, we achieve a mixture of these 2 cases at different sections of the pipeline across the entire length of the drive. So we did a sensitivity analysis in which the pipes are partially lubricated and the bore has partly collapsed. I will go in more detail about this in the next slides. It is important to note that at any stage of the calculations for the three above cases, the jacking forces cannot exceed the structural capacity of the pipe or the capacity of the interjacks, if we are using any of them, or the capacity of the first wall. Depending on the project, you have to assess which element is going to be critical for the limiting load case. The Pipe Jacking Association has a design guide, very comprehensive guide with several equations and worked example for various ground conditions. And this is what was used to calculate the ground stresses and the shear forces as well that is mobilized during the construction. The diagram here shows the stresses acting around the pipe. You have the horizontal stress, the vertical stress here, total vertical stress here, and the horizontal stress here, and shows the main failure mechanism, which is this block of soil moving down, vertically downward towards the tunnel. I'm not going to delve further into the equations to calculate the vertical and horizontal stresses for each drive, but I'm going to give a brief overview of what the parameters, what of the variables being described in this picture. So we have DE, which is the external diameter of the pipe. We have sigma V, which is the total horizontal stress. Of course, if we are dealing with a high water table, we will need to then compute the effective vertical stress by subtracting the water pressure at that level. We have the lateral F pressure coefficient to get the horizontal stresses. Sigma H is the total horizontal stress. H is the cover of the tunnel above the crown, which is here. H1 is the depth of the water table below the ground level. And phi is the angle of friction of the soil in which we are tunneling. So this equation here is the main equation used to compute the shear forces mobilized by the pipes. We have the external diameter of the pipe again. We have the effective vertical and horizontal stresses, and then we have delta, which is a pipe soil friction angle, and this has been taken to be 0.6 of the friction angle of the soil. So for case 1, which is the fully collapsed bore case, this shear force given by this equation is mobilized for every meter of the pipe. In case 2, that is a partly collapsed bore, we only take a percentage of the shear force being mobilized for every meter of the pipe. This was based on a sensitivity analysis to calculate a reasonable worst case scenario for the percentage of the bore collapse. If I remember correctly, we did 30%, 40%, 50%, and 60% of the bore collapse. And we made an engineering judgment on there based on that. Then we have case 3, which is the fully stable bore. We use the shear resistance of the lubricant because what's important to understand is there is shear forces, right? But what's changing is what is contributing to the shear force. In case 1, it's fully contact with the soil, so the soil is providing the full frictional force. Whereas in the fully stable bore, the friction is being provided between the soil and the lubricant. And in the case 2, which is the intermediate case, the friction is being provided by a mix of soil interface and lubricant interface. And that is why we reduce the frictional force by percentage accordingly. So for this case, the shear resistance of the lubricant was estimated to be 0.25 kPa. But there's one more thing to consider, especially for GRP pipes, because these are fairly light pipes compared to the traditional ones. So they will literally float in this lubricant when they are placed into the excavated tunnel. So it will probably become fully buoyant in the bore, and this will lead to an additional frictional resistance between the pipe and the bore. This additional frictional resistance was given by this equation here, m equal to mu times n. Mu is the coefficient of friction, which was taken to be 0.25. and N is the buoyant weight of the pipe, of the GOP pipe. In this case, one pipe segment had a weight of 24 kilonewtons. Just to give you a bit of perspective, if we were dealing with a concrete pipe, this buoyant weight will be somewhere around 74 kilonewtons, more than three times more the weight than this one. This slide shows a summary of the calculated forces. The first two components are fixed. We have the face pressure, which is based on the applied pressure to the slurry, while the frictional resistance along the micro-TBM is based on the length of the micro-TBM. So these are fixed components. The frictional resistance along the pipe is given per meter. And if we want to obtain the total jacking force for the pipe, we can multiply this by the length of the drive. Length and drive AB was 143 meters long, and drive AC was 78 meters long, if I remember correctly. We can also observe that the highest shear force per meter occurs in case 1, because we have full contact with the soil. The lowest value is for case 3, and the shear force per meter for case 2 is somewhere in between the two. As you can see here, for case 2, we are using, I have showed the value for 40% of the bore collapse. This table shows a summary of the number of interjacks that would be required for each case. So for case 3, which is kind of the safest case, well, not safest case, but lowest load case, we didn't have to use any interjacks. For 40% collapse, we needed 1 interjack for drive AB and 0 for AC. And for the fully collapsed bore, which is not going to happen in reality, we needed 2 interjacks for drive AB and 2 interjacks for drive AC. It was concluded that 1 interjack was required for drive AB and no interjacks were required for drive AC. And this was based on case 2, which considered 40% of the bore collapse with lubricant in the annulus, being the worst reasonable case during the pipe jacking following the sensitivity analysis. I believe that's the last thing, and that's the last slide. So to conclude, the GMA that we performed, it demonstrated that the ground movements that we were encountering due to the shaft construction and tunnel construction had no adverse effects on the 2 buildings. So we didn't require any mitigation for the following the GMA, because there was no damage to be expected to the buildings. Then I gave an overview of how to do the pipe jacking, how to assess the pipe jacking forces to the drives for each drive, and this we concluded that 1 interjack was required for drive AB and no interjack was needed for drive AC. That should be all from me. Thanks all for your attention and listening, and I'll take questions now.